Welcome to today's Explainer. We're jumping straight into a real journey of discovery today to totally master cubes and cube roots. But, before we dive headfirst into the really complex problems, we've got to let the engine warm up a bit. Think about a car engine for a second. You wouldn't just turn the key and immediately slam it into fifth gear, right? It needs a gentle start. Well, your brain works exactly the same way with new mathematical concepts. By warming up first, we actually lower the cognitive load, and honestly, we build up that essential confidence. So here's our roadmap, the 5 levels we're going to conquer together today. Number 1, what is a cube? 2, properties and patterns. 3, the Hardy-Ramanujan number. 4, understanding cube roots. And finally, number 5, prime factorization. Let's get into it.
Level 1. What exactly is a cube?
Okay, so in mathematics, cubing a number literally just means multiplying it by itself 3 times. We denote this as x to the power of 3. So if we take a number, let's say 7, and we want to find its cube, we absolutely do not multiply 7 by 3. No way. Instead, we multiply 7 times 7 times 7, which gives us 343. It's just the same number repeating 3 times.
Notice how perfect cubes, some people call them cube numbers, are just formed naturally from this process. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and so on right up to 5 cubed equaling 125. These results, 1, 8, 27, 64, 125, these are perfect cubes. Now, let me challenge you for just a second. Look at a number like 81. Is 81 a perfect cube? Well, think about it. 81 falls right between 64, which is 4 cubed, and 125, which is 5 cubed. Because it sits right there between those whole number results, 81 simply cannot be a perfect cube. Makes sense, right?
All right, moving on to level 2, special properties and patterns. These are basically your mathematical cheat codes. There is such an incredible logic to these shortcuts. If a number ends in 1, 4, 5, 6, 9, or 0, its cube is going to end in that exact same digit. 4 cubed is 64, ends in 4. 5 cubed is 125, ends in 5. But take a look at the exceptions at the bottom. They kind of act like a mirror. If a number ends in 2, its cube ends in 8. And if it ends in 8, well, the cube ends in 2. The exact same thing goes for 3 and 7. They just flip. So if you're looking at a massive number ending in 8, you instantly know its cube will end in a 2. Bam! No heavy lifting required. Now here's a secondary shortcut that is just as reliable. Even numbers will always result in even cubes. Odd numbers, they'll always result in odd cubes. It is really that simple. Like 2 is an even number and 2 cubed is 8, also even. 3 is an odd number and 3 cubed is 27, totally odd. So if you're ever on a test and asked if the cube of, say, 7,432 is odd or even, do not calculate it. Just look at the last digit. It's a 2, right? An even number. So the entire cube must be an even number. Okay, there's a bit of hidden magic in this math. Look at this beautiful pattern. If you add consecutive odd numbers, they perfectly align with the sequence of cubed numbers. Check this out. The first odd number, 1, is 1 cubed. The next 2 odd numbers, 3 plus 5, equal 8, which is 2 cubed. The next 3 odd numbers, 7 plus 9 plus 11, equal 27, 3 cubed. Adding 4 consecutive odd numbers gives you 4 cubed, and so on. It's like this infinite, perfectly structured mathematical staircase. Mind-blowing, right? Let's take a quick detour. Easter egg, the Hardy-Ramanujan number. Let's just take a quick breather here with a really cool human story involving 2 absolutely brilliant mathematicians, the legendary Indian mathematician Srinivasa Ramanujan and his colleague G.H. Hardy. So one day, Ramanujan was very ill, and Hardy went to visit him. Hardy arrived in a taxicab and casually remarked to Ramanujan that the taxi's number was 1729. Hardy was like, it seemed like a rather dull, uninteresting number, and he really hoped it wasn't a bad omen. But Ramanujan immediately perked up. He told Hardy, no, 1729 wasn't dull at all. In fact, it was incredibly fascinating.
See, Ramanujan instantly recognized the unique mathematical beauty of 1729. He explained to Hardy that 1729 is literally the absolute smallest number that can be expressed as the sum of 2 cubes in 2 completely different ways. Look at this. 12 cubed plus 1 cubed equals 1729, but also 10 cubed plus 9 cubed equals 1729. This incredible numerical coincidence is exactly why 1729 is famously known today as the Hardy-Ramanujan number.
All right, back to business. Level 3, understanding cube roots.
So far, we've basically been building numbers up, right?
We multiply them to make them bigger. Now we're going to learn how to throw the machine into reverse. A cube root is simply the exact reverse operation of a cube. If 4 cubed, which remember is 4 times 4 times 4, equals 64, then the cube root of 64 brings us right back down to 4. Mathematically, it's the equivalent of raising a number to the power of 1/3. We use that special radical symbol with a little 3 tucked in there to signify that we are digging down to find the original root number that got cubed.
Now for the main event. Level 4, solving with prime factorization. This is kind of our boss fight. Let's see how to tackle really complex numbers using a completely foolproof method. When we did square roots before, we grouped prime factors into pairs. But since we're dealing with cubes here, we need to think of these numbers a bit differently. We're looking to create triplets. Step 1, you divide the big number down by the smallest prime numbers possible. Step 2, you group those identical prime numbers into sets of 3. And step 3, you just take one number from each completed triplet and multiply them together to find your cube root. Easy!
But let's look at an example to see what happens when things don't go perfectly. Take the number 53,240. If we prime factorize it, we get this beautiful triplet of 2s and a beautiful triplet of 11s. But we're left with a single solitary 5. That 5 is basically the third wheel on a date. It's ruining the whole dynamic and preventing this number from being a perfect cube. So how do we fix it? Simple. We just divide the entire original number by 5, kicking that third wheel out, and boom, leaving us with a perfect cube.
Let's apply this prime factorization logic to an actual physical space with Parikshit's cuboid problem. Imagine Parikshit has a small cuboid block with dimensions of 5 centimeters in length, 2 in breadth, and 5 in height. The big question is, how many of these specific cuboid blocks does he need to stack together to form one giant perfect cube? To solve this, we don't even need to guess. We just complete the triplets. Our current prime factors from the block's dimensions are 5 times 2 times 5. Let's group them up. We have 2 5s, so to make a triplet of 5s, we need exactly one more 5. And we only have a single 2, so to make a triplet of 2s, we desperately need 2 more 2s. So here's the final answer. We need 1 5 and 2 2s. If we multiply what we need together, 5 times 2 times 2, we get 20. Parikshit needs exactly 20 of his original cuboids to build a perfect cube. We didn't even have to try visualizing stacking physical boxes in our heads. We just trusted the math of completing the triplets. How cool is that? Before we wrap up today's explainer, I really want to leave you with a provocative thought that honestly stumps people on tests all the time. Ask yourself, can the cube of a 2-digit number ever be a 3-digit number? Well, think about it logically with me for a second. What is the absolute smallest 2-digit number that exists? It's 10. Right? And what is 10 cubed? 10 times 10 times 10 is 1,000. 1,000 is a 4-digit number. So the smallest possible 2-digit number creates a 4-digit cube. That literally means it is mathematically impossible for the cube of a 2-digit number to ever be a 3-digit number. But what happens when you move to 3-digit numbers? How massive do those cubes get? Well, once you learn the rules of the game, the math kind of answers itself. Keep looking for those patterns, and I will see you in the next explainer.